question, and then we'll have some refreshment. Thank you. Thank you for coming.
Thank you. Thanks.
And we also have a pointer today.
Okay.
It should be working. Yes, and yeah.
Okay. Thanks. Hi. So my name is Neave. I'm originally from Ireland, and I actually studied maths and network science for my PhD at Imperial under Mauricio Barahona, who you might have heard of. But then after my PhD, I took a bit of a leap, and I followed my sort of secondary passion to go and study at the Harvard Kennedy School with Harry Heisman. He's a very well-known economist who works really on modeling the economies of developing countries. And so that was a bit of a baptism of fire because I hadn't studied economics formally previously or development. And so following that experience, I developed my own kind of expertise at the intersection of complexity science, network science, and now particularly with a focus on the development, on the economic development of cities. So my group is quite broad, and we do lots of different things. But one of the areas that we focus on is developing mathematical and network science tools to answer questions that we come across for which there aren't already, methodologies available. And so one of the big kind of open questions, or an area in which we found there was few tools available to us, was the kind of topic of network comparison. This idea that you would want to have two networks, potentially they would have the same nodes, they would have different structure, and how would you compare those two networks? And of course, it depends exactly on what it is you want to compare, but nevertheless, the toolbox to probe that type of question is actually quite sparse. Despite the fact it's a quite sort of, obvious or easy to pose question. Okay, so I'm presuming all of you are familiar with the concept of network communities, the idea that networks exhibit sort of groupings or clusters of nodes. There are many different ways of detecting communities, and there are infinite numbers of different types of networks that you might want to apply community detection algorithms to. I think we saw in the previous presentation an application of community detections to network data. Right, so as I was saying, there is a vast literature on community detection. This is something that's ongoing, and this is a very kind of vibrant community of people who work consistently on improving and offering new directions when it comes to detecting communities in networks. Okay, so in our particular case, our sort of baseline is that we're going to have two networks, and they are node aligned, which means they have the same set of nodes. And in our particular case, we're going to assume that we know what the communities are. We're actually not going to tackle the question of how we detect those communities. Our method that I'm going to propose is somewhat agnostic as to the method that's used. So I'm going to come back a bit more specifically on that point later. But our general setup is that we have a pair of so-called node aligned networks. Okay, so in the literature, there are a couple of methods that are around to compare networks. So when it comes to general comparison, not particularly comparing clusters, but comparing networks in general, some of the more well-known ones are called Jacquard or graph edit distances. And the general idea is really simple. You just count the number of edges that you need to add and subtract to transform one network into another. Now, I'm sure some of you can already think of reasons why that might be overly simplistic or perhaps not very useful at times. Another one, which again may be intuitive to some of you who've done some work on networks before, is comparing the second smallest Laplacian eigenvalue. Again, that tells us something general about the connectivity of the network. In some particular applications, that could be a useful thing to compare. When it comes to the comparison of network communities, particularly, which is the question that we're interested in, there are actually very few approaches in the literature. There are a couple of papers that do ad hoc types of things. The more, if you ask someone what's the sort of state-of-the-art method, there are variations on so-called mutual information metrics. So these are really metrics coming from statistical physics, and they use entropy in order to compare the sets. So they implicitly ignore the structure, and they're just comparing the two partitions in terms of sets. And so the method that we are going to develop here aims to tackle that issue, right? Aims to move away from a set-based comparison towards a comparison of the underlying network structure. Okay, so I have a question. So network A is our network of interest. What do you think, which of the other networks is the most similar to A? There's a couple of right or wrong answers, so offer some ideas. Yeah. B, yeah. C, yeah. C, pretty good candidate. Yeah. Any others? No.
Be careful with windows. Is that just you?
Oh, that's like a window. You see that? Yeah, but E is also reasonable. There's some similarities for sure. Okay, so what we're going to do is we're going to have a little look at what these various distances give us. Oh. I think by moving the Zoom box, I've somehow all right, there we go. Okay, so the various network comparison metrics actually give different answers here. So the Jacquard suggests that B is closest to A, which is this graph edit distance, right, where you're adding and subtracting edges. C, which is a very intuitive choice, the spectral method picks C. That's a very reasonable answer, as being the most similar. Then normalized mutual information, which is the one that is the one that is most tailored in some ways for communities, thinks that A is most similar to E, but it can't distinguish B and C because it can't see the internal edges. So it thinks that B and C are identically matched to A. Okay, so we see here that we have a proliferation of responses, but there are some clear issues with the normalized mutual information metric, given that it can't really tell the difference because it just doesn't pick up any information. It's just purely comparing sets and nodes and not edges. Okay, so what we want to do is develop a new method which does take into account the underlying structure. So I'm going to take a step back for a second and think about, okay, so there are different ways of detecting communities. Many of you will be familiar with some of the, I'm going to call them the classic methods, which rely on a so-called quality function. So a quality function is a function that takes in a partition and a network, and it gives you a sort of score of how well that partition is, represents that network in a sense, right? So this is a very well-known quality function called modularity. There are some issues with modularity, but nevertheless, although I'm going to show you our method using modularity, our method works for any quality function, so it's not particular to modularity. So you don't need to be concerned that if you, for whatever reason, don't like modularity or don't like various other quality functions for perfectly valid reasons, that this method is somehow intrinsically relying on them. It's not. Okay, so we have a quality function, and it takes in a partition and a network, and it spits out a score. Okay, and what community detection does generally, right, is it's a sort of two-step process, right? You have your quality function, so you have modularity or info map or some other quality function of your choosing, and then you have a search algorithm, right? So one of the famous search algorithms is Neave, and what it does is it looks for a partition that maximizes this function. So there's a sort of process by which it sort of searches for the maximizing partition. So in our particular case, we're going to have two networks, A and B, and we're going to have the maximizing partition for each of them separately, right? So so our sort of input is network A, network B, and partition A, partition B. Okay, and so what we're going to do is we're going to develop a bidirectional score or distance, right? So we want to know how well does one network describe the partition from the other and vice versa. So how do we compute this? So we can see here our first distance metric, and on the top, we're just going to evaluate the modularity. So you see F, this function F. This function F can be modularity or any other quality function. We're going to evaluate the partition from network B on network A, and we're going to divide that by the quality of partition A on network A. So you can see that if B is very well described by A, that's going to be a very small number, right, the ratio. And so we can do this in two directions. So we end up with this bi-directional score, which basically says how well does one network describe the partition from the other. And so this ends up having lots and lots of interesting properties. And it also takes into account this underlying structure. So what I'm going to do now is illustrate some of those properties using a mixture of toy data, synthetic data, and real world data. Okay, so this is the kind of thing that we actually get in the end when we plot the scores that we get from the various toy networks that we already saw. So you see that we have this two-directional score. So instead of having one number, we have two numbers, and we can just plot them very simply like this. Okay, and so we can see here, for example, we can see that C, right? We see, so if two networks are closer, their score is going to be closer to the origin, so the distance is smaller. So the points that are closer to the origin are closer. And we see here that when we project the partition from C onto A, it's smaller than the partition from B onto A. So our method is basically choosing C as the closest to A. Okay, so what are the features, the general features of this method before we go any further? So it's generalizable for any community detection algorithm that works by optimizing an objective function. It accounts for the underlying network structure, so it implicitly accounts for the underlying structure, so that's the connections within and between communities. And we'll see some more examples later of how exactly that plays out when we apply it to networks. So it can actually determine similarities or differences between networks that have they have very similar partitions, but actually those partitions kind of mask underlying differences, right? So the partitions for one could be very robust because there's very strong internal connectivity. The partition for the other might not be as strong, and our method will actually pick that up because it's looking at the connectivity. And it can also pick up the alternative scenario when we have two partitions that are very different, but actually the underlying structure is quite similar. So a really good case that we're going to see quite a lot of here is the case of nestedness, right? Where actually, your optimal partition might have quite large communities, but inside those communities there are relatively well-defined subcommunities. And if those subcommunities are there, and you have another network with those subcommunities that are, then you're actually going to pick that up. Our measure is going to be able to pick that up in a way that would be impossible if you just compared the sets. Okay, so that's the point about nested communities. So this is a particularly good method to pick up nestedness between two networks. Okay, so here we're going to basically subject the method to a lot of tests, some of them very simple, getting progressively more complex. So here we just have some block models. So here we're just generating a large cohort of synthetic networks where we just have a different probability. So these are just adjacency matrices that you're looking at. And there's a high probability of connection inside the community, a lower probability outside. And as you can see, as we increase the number of the network, the internal connectivity decreases. So the communities become less clear. And so we can see in our plot that when we compare network 4 with network 1, they're quite distant, right? But as the networks become more defined, so A2 and A1 are the most similar. So this is more kind of seeing, okay, does the method pick up the really simple things that we would expect it to? And then we can over time, we can ask it to do slightly more complex things. So here we have a second case where we have, again, we have different kind of challenges in a sense, right? And we can see this sort of nested behavior coming out, right? So we can see that, along the x-axis, we can see that, B2 is the most similar to B1, but as we subdivide the communities over time, we see that actually in one direction, they're very similar, right? So when you project B1 onto B5, you get quite a low distance, but when you project B5 onto B1, you get a much larger distance. So it's picking up this, we're beginning to see evidence of this kind of nested behavior. Okay, and here's a clearer example of that, right? So here we have an example where if you project C1, so the partition of C1 onto C2, you get a smaller distance if you project C1 onto C3 compared to C2, because C3, although its maximal partition has 4 communities, it has this nested structure. So it has this middle community, which doesn't show up in the maximum, but it's nevertheless there in the network structure, and the method actually picks this up. So the method is showing that, the distance is smaller between when you project C1 onto C3 compared to C2. Okay, so why did we do all of this, right? Why were we interested in this question to begin with? How did we actually, come to study this very particular comparison of network communities? So one of the major areas of research that I'm involved in is modeling, let's say, regional industrial diversification and growth, right? So this idea that, so there's a sort of large community of people, or a large kind of academic community, who think of economic development very much as a path-dependent process, right? This idea that the skills and capabilities embedded in a place, in a region, in a city, very much determine the kind of things that can grow there in future. And so some of the tools that are used to model this process of path-dependent diversification are these industry networks. So here, the nodes are industries, and the edges are job transitions between industries. So you can imagine, if you're trying to understand what industries are similar in terms of skills to those that I already have in my neighborhood and my city, then by looking more generally at job transitions between industries, you can get a pretty accurate gauge on similarity of skills, right? So we kind of infer that if people move between industries, they require similar skills. So we can use these networks as the kind of backbone of a whole suite of models that try to predict effectively the growth of industries and the entry of industries into regions and cities. And so we were working with these networks, and just gonna skip over some of these points. Okay, so we've been working with these networks for a while, and so when you're thinking about developing, I'm not going to go into detail into the sort of apparatus behind the modeling, but if you think about trying to build a model, right? So you're trying to use the network structure in order to predict, what is going to happen in a city over time, given the industries that it already has. And so you want to know, okay, well, for a new industry to appear, what kind of skills need to be already present? How far in the network matters, right? How distant are the skills that can be useful to this industry potentially? And so we can see that the network structure inherently governs that process to some extent, right? So if your city is located in a part of the network that's very isolated, right? It's in a community that's disconnected from the rest of the network, then its ability to source skills, right, in related sectors is more limited. So previous models neglected to some extent this more global structure of the network, only looking very much at, say, nearest neighbor effects. So we developed some new models that take into account more explicitly the global structure of the network. And we actually use communities in order to define, in a sense, what is the skill radius at which industries and cities could reach in the network. So, what is the distance, the skill distance that would be useful to industries in terms of growth? Okay, so the question that comes out of this is, what is the right scale, right? How deep into the network might an industry want to reach in terms of sourcing workers that have similar enough skills that would be useful to them in growing their industry? Now, of course, we've previously mentioned modularity maximization as a way of detecting communities, but as I'm sure many of you are aware, that's a little bit simplistic, because you're quite likely not only to not have only one scale at which communities exist, but you're likely to have a sort of nested structure, as we've mentioned, and you're likely to have a sort of continuum of partitions that have varying qualities, but nevertheless are to some extent valid descriptions of the structure of the network. So we can use the called multi-scale community detection to kind of extract partitions at these different scales. But here we have a resolution parameter, which is effectively a time parameter in a community detection algorithm. So when we think about high resolutions, we think about a sort of, well, I'm not going to go into too many details, but this refers to a community detection algorithm, which is based on random walks. And if you let the random walker search the network for a long period of time, they're going to find intrinsically larger communities. So the large resolution parameters correspond to partitions, which have few but large communities. On the other hand of the scale, for small resolutions, which is small time scales, you're going to find lots and lots of small communities. So you're going to have partitions with many smaller communities. And so actually you can extract loads of really interesting information from the network by looking at the partitions across all of these different scales. So what we did is we incorporated, and I'm not going to go into too many details because this paper is not the main source, not the main presentation here. But what we did is we kind of combined that idea of a multi-scale structure with some existing models in order to estimate what is the intrinsic scale at which industries tend to source skills from other sectors to boost their own employment growth. And so what we found in the case of the UK is that there is a sort of characteristic resolution or partition, and we see some interesting things. For example, in services, quite a lot of services emerge, right? So, one shouldn't really necessarily think about health and education as distinct labor pools. They actually can be thought of as integrated labor pools when it comes to boosting employment growth. And other things like, finance and real estate, publishing and software, all of these things actually in our model come out as being part of integrated labor pools and are not distinct sectors in the way that they're coded in the official industrial classification. Okay, so that is one of, so this work, which is separate work, was really the sort of motivation, because we came to understand that the modular structure of these inter-industry labor transition networks, that the modular structure was very important and it was governing many processes on these networks. And so what we wanted to do is we wanted to compare the structure. So we have collected these networks for quite a large number of countries. So they're actually really difficult to make because you need individual level administrative data and you need to follow workers over time. So to see them hopping between jobs. So you need to develop a partnership or a contractual agreement with a national statistical agency and probably have somebody go in and work in there to put this kind of thing together. And so we did that for a couple of countries, and then we partnered with some other groups who had done it for other countries. And so we collected quite we currently have about 10 of these. Some of them are in different industrial classifications. I'm only going to show you the work for 5 of them here. But the idea was basically to look and see, how do these networks differ across countries? Because you can actually learn some really, really interesting things from that type of information. So imagine you're an industrial policymaker and you want to know, okay, so many things that policymakers do, they don't necessarily pick particular industries and say, I want to bring this industry into a region. It's a little bit more subtle than that. They want to create positive spillovers between industries, right? They want to create ecosystems where firms talk to each other and they benefit from each other's presence. And so what's really interesting to them is to understand what types of firms kind of benefit each other when they locate together in space. What kind of firms, share workers? Can you learn from, industries that tend to share lots of workers in Germany, but they don't in Ireland? So that's the kind of information that we were hoping to glean if we could compare these networks in a robust way. So the whole reason for developing this methodology, although it's general for any type of network and any type of optimization criteria, that was our sort of underlying motivation. Okay, so these were the countries that we have. As I mentioned, we constructed Ireland and the UK, and we have procured Sweden, Germany, and the Netherlands from colleagues. Some of them are actually available online, openly. And the idea is to compare the structure. So we can see, here we just have some very simple visuals and we can immediately see some, interesting information. So what it turns out is that Ireland, and to some extent the UK that's not shown there, are quite modular, right? And so there's actually a lot of isolated clusters that don't seem to share labor massively with other sectors. Whereas the Netherlands, Sweden, and Germany are much more integrated. So they have about 5 to 6 large clusters each. which is actually really interesting, not something that we ever would have necessarily expected before we compared the data. And so we obviously want to do this in a much more, robust way. And so we can plot, right? We can plot just the pairwise comparisons of the various different networks. So as I mentioned, so this red dot here, Germany and the Netherlands are actually the closest in structure. And they're both pretty similar to Sweden, right? So these three sort of Nordic-ish countries all are pretty similar, and they exhibit these large integrated clusters. So that means their labor market's actually pretty well functioning in the sense that you have a lot of churn between sectors. And it turns out the Irish communities are pretty well nested inside of Germany. So Ireland looks like it's much more modular, and you could never tell by just eyeballing the networks. Obviously, eyeballing networks is never a good idea in the first place, but you wouldn't have been able to tell without this methodology that actually Ireland's communities are really well nested inside of Germany's. They're subgroupings. And the UK is really dissimilar from everyone else. I mean, yeah, that's maybe not that surprising. But the UK's network really is not nested at all. It's doing its own thing. So that's really interesting, right? Because this is all the same industry classification. And it's telling us that workers are moving quite differently between sectors in different countries, particularly in Ireland and the UK. Right, okay, and the UK is nested to some extent inside of the other countries as well. Okay, so that's the sort of there's obviously more stuff in the paper, but I didn't want to go into more details here. We've also applied this to the multi-scale version. So I just showed you the kind of comparison of a single partition for each country, but we've done the multi-scale version in the paper. But what is the next big question? So the next obvious question, and something that we've been working on, is this notion of comparing a single community, right? So here we're comparing a whole partition. But for example, we have this question. So it seems to us, for example, the finance sector is really isolated in Ireland. And we'd like to know, is it as isolated in the other European countries, for example, right? And various other questions like that. We are interested in not comparing the full set, but knowing in much more detail, right? What are the individual community level comparisons? So we have a particular set of nodes, and we want to know, how similar is the connectivity structure across the different networks. For reasons that are quite technical, our method here takes advantage of using the same null model on the numerator and denominator, so we can actually divide them by each other. So the method takes advantage of this particular feature. That makes it's much more complicated in this single community case, but that's something that we have begun to think about. Okay, so summary. I don't know. I can't see the time, so I'm assuming. Am I okay?
I'm sorry, no, I have to go and get the pizza. That's why. I would say we still have 5 to 10 minutes
For questions.
No, if you have.
No, I'm done. Yeah.
Okay. No,
I couldn't see the clock.
Then we
I
have
didn't
15
know.
minutes to question.
Okay, good.
Thank you so much. Then. Oh, sorry.
Yeah.
Sorry, I was.
Well, I just have the summary
planning out
slide
because
and
I
then.
need to, like, but lots to do this. But no, so like, so then thank you. Is that?
Yeah.
Sorry.
No.
Thank you.
Oh, I should mention that this work was a collaboration between Daniel Starlino, who was a postdoc of mine, Matty Landman, who just graduated for a PhD in the last couple of weeks.
Sorry, I have many duties in today, but so now we have 15 minutes for questions. So yeah, start. So earlier we had a presentation on fitness complexity in the labor space and labor and space. So I wondered maybe if there's a connection with that. There's the economic fitness and complexity literature, and they have been studying also a case where you have fitness and complexity for jobs and skills. I'm just rephrasing what was presented earlier on. So I don't know if that's an option in terms of potential understanding of the mobility. So whether there are, I don't know, transition may depend on fitness, I assume, and skill acquisition. So it could be,
I mean, the fitness and complexity, I mean, there's very much a common underlying understanding of how regions develop, right? This sort of capability-based development model. So they emerge from like a common conceptual.
Basically, you don't need an extra complex like fitness measure to understand the development of the skills. Okay, this is pretty. I'll have to go and collect the pizzas, otherwise, yeah. Yeah.
So the data, these networks, they are worker transitions between industries. So for the detection, so of course, so our method is agnostic to what quality function or what community detection algorithm you use, right? So, but we used Markov stability in order to, detect communities. So that's based on random walkers. But that's just a sort of example. It's not inbuilt into the comparison metric. Exactly. Yeah. Has anyone ever needed to compare some networks and thinks that something like this could be useful? It seems like a pretty classic question, right? But no. Yeah. So one of the things we're interested in is partnering with people who might have data sets that we could apply this to, for example. So anything that is, slices of, so you could certainly think about applying to time slices, but then, anything that really has the same nodes and different edges, right? So we talked to Renaud about doing some stuff on brain networks and things like that that have different states and things. But yeah, I mean, in theory, there should be lots and lots of applications. So, yeah, that was one of the, not reviewer critiques, but like later critiques, which wasn't that helpful. That, we should have put in a lot more examples. Yeah. We're definitely, certainly, if any of you, or if anyone is running master students, or, what I mean, it's certainly a project that, could be a good project for a master student. The same nodes, yeah. So yeah. Yeah. I mean, I think this is probably generalizable beyond even the cases that we've put in the paper. So it's something we haven't done yet, but we have been in some discussions. It's thought that the concept of doing the two directions is probably much broader than even just doing with the optimization functions. Because some, more recent community detection algorithms don't take that route. So that's the question. Yeah. I mean, obviously there's a couple of papers in here, but the main paper I presented is the comparison. Only because I think that it is a more general tool, and so the other work that I had in there about the labor networks is a bit more niche in terms of like the community. Yeah. But yeah, it's published in EPJ, so anyone, you can have a look at the details. There's a lot more stuff in the paper. But yeah, I thought that was enough for today. And my group does a lot of different things. So I joined UCL like a few months before the pandemic, which isn't really ideal. So I'm not very well integrated into UCL still. I still feel quite new, which is weird. But my group does lots of different things. So we do stuff in economic development of cities. We do quite a lot of mobility things with, say, mobile phone data and development. We do this network stuff. I do lots of things on the informal economy, and lots of different topics in development, and then all sorts of random things as well. So definitely check out some of our work. And yeah, I need to actually update this slide. I guess we're done. I think you've all had a very long day. Thank you.